The uncertainty principle. Yes, we will finally get to touch on what the uncertainty principle is with this nice example. This is problem 1.9 out of Griffiths. A particle of mass m has a wave function psi of x of t is equal to big A e to the negative a mx squared over h bar plus it, where big A and little a are positive real constants. Let's be mindful of this function because it will appear again, and be mindful explicitly of this x squared. You'll see why in just the next chapter, actually. So for part A, we want to find big A. Remember, we do this via normalization. B, for what potential energy function v of x is this a solution to the Schrodinger equation? Remember, we have the Hamiltonians making this equation, and the Hamiltonian was an energy operator. So we needed a kinetic term and a potential term, so hence the potential energy function. Here we're solving the Schrodinger equation kind of in reverse. Normally we're given the potential and finding out what the wave function is, but for this example, we're using the wave function to verify what the potential is. Part C, calculate the expectation values of x, x squared, p, and p squared. Well, we certainly have seen the expectation values multiple times already, and they will continue to be a part of the theory really throughout the whole course. And then finally, in part D, we wish to find the standard deviation in x, the standard deviation in p, and is their product consistent with the uncertainty principle. This is going to be a long time, or a long bit of work, but we can show some nice shortcuts such as using Ehrenfest's theorem in part C, and show the Heisenberg picture that was established when he was first making his matrix mechanics approach, and then we could see how we can kind of generalize his original approach to any observable period. But yeah, let's dive in. So solution for this, well, in part A, of course, we know we needed to use the normalization condition, which of course we have to use 1 is equal to the infinite integral of the probabilities. So the probability density here is psi star psi. Here's what we have, psi star, the complex conjugate. Notice we have a negative I here versus the positive I on this side. So after you do that and you distribute it, you get your a squared here. Since it is a real constant, we don't have to use the magnitude squared. Saves us a little bit of notation. But you see that the exponentials combine their arguments due to their properties, and the time component cancels out. No big deal. In our next slide, we see that we have 2a mx squared over h bar. Notice that we have two copies of the same argument. Notice only the x variable is left. So we can set this up as our classic Gaussian, since we have a negative and an x squared in the argument of the exponent. And that's what we do here. Once we set it up into a proper form, splitting the integral in half as far as bounds are concerned, so 0 to positive infinity, but doubling it. And this allows us to form match with the tables in the book. Easy enough. Find out the parameters and plug everything in. This time our parameter in the square root is a little more chunky. Our n is 0 again, so we can plug it through. If you have questions how to do that, just send me a message and we'll figure it out. Then we just simplify on based on what the form reads, and let's run it through. After here, we throw that pi in there, no big deal. And again, we have to realize that the normalization condition, we have to be equal to 1. So now we can just solve algebraically for a, and find out that our a is equal to this fraction 2am over pi h bar to the 1/4 power. Okay, no big deal really, but just be aware that this is a messy constant. But again, physics is not always nice and pretty in actual examples, so we just have to be aware of what we're calling what. Part B though, we have to plug this wave function into the Schrodinger equation and solve for the potential energy function v of x. If you don't recall the Schrodinger equation, I have it written out here. And in my approach, it's easiest to find out what the derivatives are before substituting before substituting them into the equation, because otherwise this gets messy real quick. But let's note here that since we are having to take derivatives and we notice that the wave function is an exponential, we just get some factor times the original wave function itself due to the chain rule. And so when we simplify, let's make sure to simplify them in terms of the initial wave function, which is what we see in the time derivative here. You know, we know that the derivative of an exponential is the exponential. You use the chain rule, you get negative AI. And so what I'm saying is that we still see this initial wave function here, and we'll just put that back as capital phi or capital psi, but with the chain rule constants out front. And what we'll see is that makes comparing and finding a solution a little bit easier when we're having to simplify the algebra. Okay, that was our time derivative. Moving on to our positional derivative. That's the first derivative. Again, chain rule takes it into account. Our second derivative, you have to be a little more careful because of this leftover x. Now you have a product rule, and that's what we see in the parentheses here. Again, we know what d by dx is, that's 1, and we factor the psi out to the right-hand side. Here we're left with x times the derivative of psi, which we simplified to this thing. So we get x times this constant here, hence the x squared in that parentheses. So, it can get a little weird trying to consolidate all these things and using old parts in new places, but it saves so much time when you can use old results than having to reformulate them all. So now that we have our derivatives, let's go ahead and plug them in. All right, so here on the left-hand side, we had the time derivative. So in the bracket, we put our time derivative factored form in. And here we have the positional derivative. Okay, you notice how every single one of these factors has a factor of the wave function associated. So that's why we want to simplify it back in terms of the wave function, and we'll see the cancellations later. But as you see, we get a whole host of cancellations here with the constants. Be very, very careful with the algebra. It can get messy really quick. Clearly here, when we distribute IH bar, we get I squared, which is -1. So the double negatives here cancel out to a positive, and we're trying to isolate V times psi because we're trying to solve for V itself. Okay, so we bump this bracket over to the left-hand side, and we're just simplifying down. Notice that we still have to be careful of this HA term here, and so we'll just multiply that into the parentheses, and we get a ha 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 moment. I don't think that was intentional, but it's kind of funny. All of them cancel. H bar A and H bar A here cancel. H bar cancels with that denominator, so we're really good. Notice here that we can do this one of two ways, where we compare the coefficients to the wave function, which I did in purple, or we can just cancel the wave function on both sides. Either way, you're totally fine. I'm just hesitant on canceling wave functions because in quantum mechanics and other classical theories, we have to apply an operator onto the function, so canceling those things doesn't always work out well. And we'll see more examples of that when we get into chapter 3 of how to deal with that. Nonetheless, this is our potential energy function where it's 2a squared mx squared. Notice again that this sets up ourselves perfectly to use Ehrenfest's theorem because the potential energy is of order 2. It is a parabolic, and this looks like a potential that we'll see in chapter 2. Again, feel free to memorize this particular setup because it will get used again. Okay, enough on that. Let's get to expectations. So the expectation value of x, again, this one's kind of easy because we love abusing the fact that this turns into an odd integrand over symmetric bounds, so symmetry dictates that we get a zero integral. Wonderful, easy enough to deal with. X squared, however, is a little more difficult, and we're going to have to be careful. And what we see here is that we have to set up the integral to form match, much like we did in part A when we tried to normalize something. So let's see what our new parameters for the x squared term actually makes the integral equal to. All right, so here we can plug in everything from the parameter in the table list. Notice that we have a bigger power this time. Instead of n equals 0, we have 2, so all of this works out. Be very, very careful on simplifying this. I try color coding it to make it seem as easy as possible, but let's note here that with this we have the square root here, and that came from the fact that a was equal to the 1/4 power of all those constants. So if you square a 1/4 power, that gives you a 1/2 power, which is the same as a square root. Cool, nice. And then we see everything else just wants to start canceling away and eating away. We have a factor of 2 here, factor of 2 here, and we have 3 factors of 2 from the cube that'll come in this step. So I'm trying to color coordinate which ones join together and which ones cancel together. You see the pi here ends up going into the pi of the green, which we see a cancellation here and here. These 2 factors of 2 cancel with 2 of those factors, leaving us with just a factor of 1/2, which is what we see simplified here. The fact that we have a square root here being cubed tells us we have a 3/2 power. And since this green radical gets reduced down to a square root, we can cancel a factor of 1/2 out of both of them, or a factor by 1/2 out of both of these since they're reciprocal arguments. So it simplifies really, really nicely actually. And this, when we factor out this 1/2, this leaves us with 2 over 2, which is just 1. So that leaves us with h bar over 2am multiplied by 1/2. That's how we get the 4. So these integrals aren't too bad. They just get carried away when we have the 4 match, and it's always the algebra that we make a mistake in, not necessarily the calculus or the quantum mechanics part. The algebra, of course, always makes or break our setup. Now, going on to the momentum, let's use Ehrenfest's theorem, where we know that we could take the time derivative of the x expectation value. And clearly, the time derivative of 0 is 0, and we get the expectation of momentum. That is so much nicer than having to do an integral with an operator. How cool is that? Saves us so much time. Alright, moving forward though, of course the squares have to be a little more difficult. Notice again that this is a momentum operator squared. So now we have 2 of the derivatives. But recall that, especially why it's highlighted in green, we already calculated the second spatial derivative of the wave function when we substituted it into the Schrodinger equation. Excuse me. So we like that, and we get to use up what we already found earlier, and we substitute that into the green bracket. What this allows us to do is simplify down pretty quickly. We like that. Makes quick work of everything. Cancel away and simplify before trying to evaluate the integral. Once we see that we're done canceling away, get all the algebra out that we can distribute this so we get a psi star psi, thanks to the 1 here, that goes to that integral, and then we get a psi star times all this stuff. And what we notice is that we've kind of already done both of these integrals, but they're in disguise. Let's see what I mean. When I color code it, I get psi star psi with an x squared here, and that is the expectation value of x squared, and the red is the constants that go on that integral. So once I realize I've already done these integrals, I have 1 from this integral, which is just due to the normalization factor, and I have 2am over h bar, which is the coefficients here that are just not adding anything to the integral itself, but I have psi star x squared psi, which is the expectation of x squared. And we already found out what that was. That was h bar over 4am, so these constants cancel out very quickly, and we love to see that. Notice here that my constants from the green are just falling through all the way, and then we're left with 2am h bar times 1 minus 1/2, which is just 1/2. So you see the 2 and the 1/2 cancel, leaving us with am h bar as our expectation of momentum squared. How cool and quick is that when we get to use old results? It saves us so much time. And now we finally get to touch on our Heisenberg uncertainty principle. So, all this work with the expectation values and measuring the spread and so on comes together here. This will be your friend or your enemy. Either way, get used to seeing this inequality. What we need for the inequality is the product of the standard deviations. So of course, use the variance, take the square root, pretty simple calculation there. Expectation of x was 0, easy enough. Expectation of p was 0, easy enough. So we're taking the square root of AMH bar, and you see in purple we have both of our standard deviations in position and momentum space. And we want to know, is their product consistent with the uncertainty principle? So is their product greater than or equal to h bar over 2? Well, let's multiply them together. Color coding it again makes quick work, both in the square root, so combine them. Quickly you see that AM and AM cancel, so it doesn't actually matter what the mass of the particle is, because they're going to cancel anyways in the uncertainty picture. But we do realize we have h bar squared over 4, which is 2 squared, so that's h bar over 2 squared, and the square root and the square cancel, leaving us with h bar over 2. We love to see it, easy enough. But what this shows is this is barely consistent with the uncertainty principle. And if we want to have a further discussion of the uncertainty principle, let's do it because it is going to come up again and again. And there is a, especially if you study signal analysis, you'll know that they have this trade-off in resolution, and that is something that will be seen time and time again in other spaces. But what we'll see later on in this book, especially, is the fact that Fourier transforms come into play when we're talking about position space and momentum space, and the tie-in to other aspects of math and physics is really freaking cool. And if you love math, quantum mechanics is definitely one of your favorite things to study. So until the next one, happy learning.